Alright, so this is the second lecture on kinetics, and we're going to start by discussing the rate law. And the rate law is very important. It's what we see a lot of times when we do kinetic studies and things like that. The goal is to determine the rate law for the chemical reaction because it tells us a lot of very important details about the reaction and how it happens. But in general, the rate law describes the effect of the reactant concentration on the reaction rate. So, it's like saying, what if we double the concentration of my reactant? Is that going to make the rate of the reaction faster, slower, or doesn't change? Or if it makes it faster, by how much? Does the rate double? Does it triple? Those type of things. So if we consider our very simple reaction again, where we have reactant A decomposing to some products. Okay, our rate law is going to be different than the expression we've been writing on the previous lecture. The rate is going to be equal to, I forgot my equal sign, K, which is the rate constant, times the concentration of my reactant to some order, to some power. Alright, where K is what we call the rate constant. That's a lowercase k, so rate constant. Alright. We'll talk more about it later on. And then N describes the reaction order with respect to that reactant. And we're going to talk about reactions where N is equal to 0, is either 0, 1, or 2. Alright? And if N is equal to 0, then the reaction is what we call zero order with respect to A, or the concentration of A. And the reaction rate is therefore independent of A's concentration. All right. If you think about it mathematically speaking, if I take that, if I raise anything to the 0 power, that's just 1. So no matter what the concentration of A is inside those brackets, it's always going to equal 1. So the rate is not going to change no matter what my reactant concentration is. Now, if N is equal to 1, the reaction is first order. Alright, and that means we're going to have a linear relationship between the rate, how fast the reaction is, and my concentration of that reactant. Alright, so it's first order with respect to the concentration of A, and the reaction rate increases linearly. Now what that means is, say I run the reaction one time with the concentration of my reactant at 1 molar, and then I double that concentration to 2 molar, then my rate will also double. The reaction will be twice as fast as it was with the initial concentration. Okay, and then the last example, if N is equal to 2, then the reaction is second order with respect to A. And the reaction rate is proportional not to the concentration of A, but to the square of the concentration. All right? So rate would be equal to the rate constant times A squared. So if I doubled the concentration of A and then squared it, my rate would increase by 4. It would quadruple there. Alright, so let's look at a graphical view of what we would see for a 0 order, first order, or second order reaction. So the first graph, let's look at the concentration of A versus time. Right? And if N is equal to 0, remember that slope is change in Y over change in X. Right? And for a rate is equal to the change in concentration, we'll say change in A, over the change in time, right? So it's really the same thing. If I plot concentration over time, then the slope of my line would be equal to my rate. Now, if it's a 0 order reaction, that means that the rate of the reaction is independent of the concentration of A. So over time, I'm just going to have a straight line, and I'm going to draw it as straight as I can here. All right, because the rate will not be affected as I change the concentration of A. So this is when N is equal to 0. However, when N is equal to 1, as the reaction progresses and I form more product, I'm going to have less and less reactant, so my reaction will slow down. N is equal to 1, right? And then if N is equal to 2, there's an even greater dependency on the concentration of A. So as the concentration of A decreases as I form product, my reaction rate will slow down even more. And those lines aren't the best, but hopefully you see what I'm saying, that if it's first order or second order with respect to A, over the course of the reaction, the rate will slow down because I have a lower and lower concentration of A because I've been using it to form my product. Now, let's look at another way of looking at it, and I like this best. Here's another graph, and this time I'm going to look at my rate of the reaction. Okay, so this would be molar per second as a function of the concentration of A. Or see how it looks with the concentration of A. So if N is equal to 0 again, as I increase the concentration of A, as I go to the right, nothing's going to happen if N is equal to 0, right? No matter if A is 1 molar or if A is 2 molar, the rate is independent of it, so it doesn't change. However, when N is equal to 1, as I increase my concentration of A, as I go from left to right on the x-axis, my rate will increase because they're related to each other linearly. So it would look something like this. N is equal to 1. Because as I'm increasing A, as I'm going this way, my rate will also increase. And then finally, if it's a second order reaction, I will see an increase in the rate as I increase the concentration of A, but it'll look more like this, where N is equal to 2. Now, so if we look at the first graph, I've got a question here, and it says, in which case does the reaction rate slow down the most as A decreases? And that's going to be when the reaction is second order, because as the rate is going to slow down much faster because the rate is dependent on that concentration squared. So the answer here would be when N was equal to 2. And then the final question is, what is the rate law equal to for a 0 order reaction? Well, if rate is equal to the rate constant times my reactant A for this example to some power, well then if N is equal to 0, then the rate is equal to K times A to the first, which will reduce to K, or simplify to K. Rate is equal to the rate constant K. All right, now let's look now at how to determine the order of reaction. And this is something that we have to do in the lab. We must do experimentally by monitoring how the rate changes when we use different concentrations of our reactants. Okay? And we usually study the kinetics of the reaction at the very beginning, and we call this initial rate kinetics. All right, there's multiple reasons why. One is some reactions have half-lives that are very long, and it might take several hours or days, a couple of days for the reaction to go to completion, and we don't have that kind of time. And also usually over the course of a reaction, as it progresses, other things can start to happen that will interfere with your data. Okay, so usually we study the reaction, to about 10% completion or 30% completion, but just the initial portion of the reaction. Okay, and if we look at an example here for our general reaction where reactant A decomposes to some products, all right, just say in the lab we changed the concentration of A and we studied how the rate was affected. And what we can do here is we can see that as the concentration of A changed from 0.1 molar to 0.2 molar, as it was doubled, that the rate also doubled. This means that the rate was related to the concentration. There's a linear relationship there, right? As one doubled, the other doubled. Okay? So as the concentration of A doubled, the rate of the reaction doubled. This indicates then that the reaction is first order. All right, first order with respect to A. Okay? If it was zero order, the rate would have not changed. If it was second order, as I doubled my concentration, the rate would have quadrupled. All right, but here's first order, and therefore my rate law would be the rate is equal to the rate constant K times the concentration of A to the first. Okay? And now you wouldn't have to write that 1, obviously, but just so you see it here. And then the final question, how can we determine the value of the rate constant K for the above reaction, and what are its units? You need to be able to do this on the test, okay? I'm going to ask you to solve for the units of rate constants. It could be first order, zero order, second order reaction, but it's coming. But we can determine the value of the rate constant here just by using the data. Okay, so plug in and solve. Right? So if rate is equal to K times the concentration of A, I've got to solve for K. I can rearrange that equation and say that the rate constant K is equal to the rate divided by the concentration. And I simply can just select data from the table. Select the concentration and the corresponding rate. I'm going to use the first one, but you could have used the second row or the third row. And I'm going to plug in. So the rate was 0.015 molar per second. All right. And then the concentration was 0.10 molar. Hopefully you can see here that the molarity terms will cancel out, and I'll be left with seconds in the denominator. So I'll get an answer of 0.15, all right, 1 over seconds or inverse seconds. Okay. Usually we write that when we talk about kinetic studies, we don't leave the unit in the denominator. All right, we write it in the numerator, so we'd say 0.15 seconds to the negative 1, or per second is how we say it. And that would be the answer. All right, so now let's consider a reaction with multiple reactants. Let's take it a little step further, a little more complicated, where we have A reacting with B to yield two different products, C and D. Our rate law is still going to have the same format, where the rate is going to be equal to the rate constant for the reaction times the concentration of each of my reactants, A and B, to some order. So it's going to be some order with respect to A and some order with respect to B. Okay? And then I've got just a real example below it, and let's see from the kinetic data in the table, let's see if we can determine the reaction order, okay, for the reaction. The overall order and then the reaction order with respect to each reactant. And the way that we have to do this is we change one reactant at a time and leave everything else the same. That way we know if we see a change in the rate, it's due to that change that we made, not to something else. Okay? So for example, if we're talking about for NO2, if I look at experiments 1 and 2, right? For the first experiment, I had a concentration of 0.1 molar. For the second, a concentration of 0.2 molar. So the concentration of NO2 was doubled. But the only way that I can know how that affects the reaction is if I keep the concentration of CO the same, if I keep it constant. And that lets me know that the change that I see in the rate over here is due to changing the concentration of NO2. All right. So for NO2, I'm going to use experiments 1 and 2. All right. And then you'll see that the concentration of NO2 doubled, right? And when it doubled, that the rate quadrupled. And we can do this using an equation and formula, but I think it's easier just to see the relationship, right? When I doubled the concentration, the rate didn't double, but it quadrupled. So it increased by the square, right? So therefore, that indicates that it's second order. All right, with respect to NO2. All right, so that would mean in my rate law, I'm going to put NO2, and that M, that my exponent there, would be a 2. Now let's see if we can figure it out for carbon monoxide. I'm going to use Gregan this time. I have to find two sets of data where the concentration of carbon monoxide was changed, but the concentration of NO2 was unchanged. All right, and that looks like I can do that with experiment 2 and 3. All right. In experiment 2 and 3, the concentration of NO2 remained the same, but the concentration of CO doubled. All right. And let's see how the rate was affected. The rate was 0.0082 and 0.0083 molar per second. So basically, it was unchanged. That means that the rate of the reaction is independent of the concentration of CO, which means it's zero order. So for CO, we would use experiments 2 and 3, right? And we would see that it was zero order with respect to CO. So that would mean in our rate law we would put the concentration of CO to the 0 power, which means we don't have to put it at all. So our overall rate law would be rate is equal to the rate constant of the reaction K times the concentration of NO2 squared. All right, so it's second order with respect to NO2, and it's second order overall reaction. Now I say that because I want to show you here a difference. And I'm just going to say we have a reaction A plus B goes to product P. And that we found through our kinetic studies that the rate law was rate is equal to the rate constant times A times B. So first order. All right, so here I want you to understand that the reaction is first order with respect to A and first order with respect to B. But the overall order of the reaction is second order. So overall order is equal to the sum of the individual orders. So it would be second order. It would be the 1 here plus the 1 here. Okay, so it's first order with respect to A, second order overall reaction. And then finally, the last question is, what are the units of the rate constant K for a second order reaction? So I'm going to do this without plugging in any data. Okay, I don't think there's any need to. We can, but I want to show you a different way to do it in case I ask you on the test without any data. So if A breaks down to products P, or just products, and it's a second order reaction, then K, excuse me, rate would be equal to the rate constant times the concentration of A squared. That's just if I made up the reaction and I said it was second order. So now all I have to do is plug in the units for each thing and solve for K. Because for a rate, the units of rate is molar per second. And that's equal to the rate constant K. And then times the concentration of A squared. So that's going to be molar, because it's concentration, squared. And then so K, the units of K, would be equal to molar over second, right, divided by molarity squared. And you can see that the concentration term on top will cancel out with one of my concentration terms on the bottom. and I would be left with the units of 1 over seconds times molarity. The way that we normally write this is we would say the rate constant is equal to per molar per second. So I just put the concentration term in the front, and then I moved them both out of the denominator. All right, so the units for a second order rate constant, K, are per molar per second.